So last time we looked at what bimodules were, and the reason for wanting to look at bimodules is the following proposition. Okay, so bimodules and tensor products. So suppose I did the following. So I take the tensor product of M and N over R, and in order to do this, recall I needed to know that M was an R right R module, okay, and I need to know that N, so this is M, needs to be a right R module, N on the other hand needed to be a left R module, okay. But suppose it also happened that in addition to these structures, M also had a bimodule structure. Suppose M was not just a right R module but also a left S module, such that those two structures commuted with each other, right, or they had a compatibility. In other words, if M was S tensor R bimodule, and similarly suppose N is an SR bimodule and N is an RT bimodule. Okay, so what are all these R, S and T? Let them all be some arbitrary rings. Okay, and suppose M is an ST, SR, okay, so what this essentially means is that in addition to the bare minimum we require in order to construct the tensor product, which is the R actions on the right and on the left, in addition there is some additional structure that both M and N have. Okay, then the claim is that so here's a proposition, with this notation, then M tensor N over R is in fact it becomes a bimodule over S and T. Okay, it's an ST bimodule. So observe that's the residual, the S was there on the left and the T was remaining on the right. So the sort of the two R's get together and go away, the S and the T remain. Okay, observe if you didn't have the S and the T, we said in general the best we can say is that the tensor product is a Z module, that's all. But if you had this additional action, then this proposition says the tensor product becomes an ST bimodule. Okay, via, so what's the definition? So let's say how the actions are defined. So suppose I take an arbitrary element of the tensor product, Mi tensor Ni. Remember, anything can be written like this, though not necessarily uniquely. So suppose I take an element like this, let me tell you what the left S action is. Okay, via the following action, S acting on this on the left is just you act Mi on the left by S. Remember, M is a left S module. This makes sense. Okay, and similarly the right action satisfies the following property, that summation Mi tensor Ni acted upon by T on the right is just this element. Okay, and this is for all Mi in M, S in S, T in T. Okay, so I claim that there exists an ST bimodule structure which satisfies this property, that on a typical tensor element of the tensor product like this, the left action of S is just given by take the left factor Mi in each of those summands, just put an S on its left. Similarly for Mi tensor Ni, you put a T on the Ni portion. Okay, so the claim is such a thing exists. Now the point is, as we did once before when we talked about functoriality and so on, we can't use these as the definitions per se. Okay, the final, you need to somehow do something else to show that there exists such an ST bimodule structure which satisfies these properties. But you can't quite start with these as the definition, because then we will run into well-definedness problems, because the same element of the tensor product may have many different expressions like this as a sum of mi tensor ni's. Okay, so we don't really want to use that. So what we will do, like we did earlier, is to sort of use the universal properties of the tensor product, or rather the functoriality that we have already proven. Okay, so let's prove this. Let's first define the left and the right multiplication maps. So observe firstly that M is a left. This is a left S module, right? I mean, it's more than that. It's a SR bimodule. But at the moment, let's use only this structure. So what does that mean? It means that for any S in S, there exists something called the left multiplication map. Okay, so I'll call that map as lambda S. So lambda S is just the left multiplication by S map. Okay, so this is a map from M to M. Now, what kind of map is this? Well, it's certainly Z linear, okay, but in fact it's a bit more. Observe that if I took M and acted on the right by R, then this by definition is just S acting on MR. But remember that M is not just a left S module. So now I will use the additional property that I know about M, that it's actually a S module, an R module, and the two module structures commute. Okay, so S acting on MR is therefore, by the bimodule axiom, just the same as SM acting on R. In other words, it's just you take lambda S of M and act upon it by R on the right afterwards. Now what does this tell you? Well, this just means, i.e., lambda S is an R linear homomorphism. Okay, it's an R linear endomorphism of M, if you wish. Similarly, we have a right multiplication by T map. Okay, so similarly, let's also define the right multiplication map. This is from N to N, which takes N, goes to NT. Okay, and again, this map is also R linear for the same reason. So now N is so if I multiply on the left by R, then by definition this is just Rn multiplied by T. This is the bimodule axiom, it's R of NT. So this is just R right multiplication by T of N. So this again means that the right multiplication map is an R linear endomorphism of N. Okay, now the point is, when you have these R linear maps, then we can look at the following situation. So let me just go back here for a moment. So recall, what is it that we wanted? We wanted to construct, well, we wanted to show that there is a left multiplication map on the tensor product, which basically only acts on the first component, right? So what is this map? Well, it's sort of clear what this map is. So consider from M to M, I have the left multiplication map. From M to M, I have the left multiplication by S map. From N to N, let me take the identity map. Okay, look at this pair of maps. Okay, now we have already shown, when we talked about functoriality or how there are associated homomorphisms on the tensor product, observe that given such maps, so these are both R linear maps. Okay, the identity is always R linear. This means that there is a map called lambda S tensor identity. Okay, this is a map from M tensor N to Okay, and this is a Z linear map. So there exists a map like this. This is Z linear. Okay, and when I say there exists a map like this, what does it do? It only acts on, we sort of know what the action is. So recall the definition of this map is the following: when it acts on a generating tensor identity on N. Okay, this is for all M and M. Okay, and left multiplication by M by S is of course just SM tensor. Okay, so there is such a map definitely which acts like this. Okay, and that's that's how it acts on the generators. So if you see what is this map lambda S tensor identity on summation Mi tensor Ni, then that's just a summation of the corresponding actions. So this is exactly the left multiplication action we wanted or we claimed was there. So what we are saying is the left multiplication by S is just given by lambda S tensor the identity. Okay, now similarly, now analogous to this analysis, just look at identity tensor right multiplication by T. Okay, what is this? This is a map. This is a Z linear map from M tensor N to itself to M tensor N. What does that map do? It does exactly what we wanted to be our definition of right multiplication, which is it only acts on the second component. Okay, so we have these two Z linear maps. Now what you have to show is that, so these maps are well defined, at least that's the key point, right? This is a well defined map. We don't need to worry about showing that this definition is well defined and so on. So there are well defined maps. All we have to show is that they satisfy all the axioms required to make M tensor N into an ST bimodule. Okay, so need to show all axioms of ST bimodule are satisfied. Okay, so of course there are several axioms to check in some sense, but let me leave some of them for you as an exercise. So first you need to check that this is an left S module. So M tensor N is, let's see, what all do we need to check? Number one, it's a left S module under the given action, okay, via the action that we talked about. Okay, so via this, via left multiplication given by this, via left multiplication by S given by okay. Similarly, so this I am going to leave as an exercise. Okay, so this check, it's easy exercise. Now similarly, the right module structure is also analogous. So that's the other second exercise. Check that there's exercise 2 maybe, which is to check that this becomes a right T module via the right multiplication by an element T given by the other map, which is identity tensor right multiplication by t. Okay, so you define left and right multiplication by elements of S and T using these maps, and then you have to show that the left S module axioms and the right T module axioms are satisfied. Okay, so that's more or less easy because they are just satisfied on each individual component separately. But the key thing that we need to check is the compatibility between these two. Okay, now what does compatibility mean? It says if I take an element xi, summation mi tensor ni in the tensor product, okay, and then I act first on the left by S, then on the right by T, will I get the same answer if I do it in the other order? Okay, so let's take this element xi, act first by S, then by T. Let's check. On the one hand, this is nothing but summation Smi tensor ni acted on the right by T, but T only hits the second component. So this is just nothing but Smi tensor nit. Okay, and observe in some sense what's happened is that the S and the T have acted upon two different parts, the two different components, tensor components. So if you did in the other order, you will still get the same answer. It will just, the first step will give you nit, the second step will give you Smi. That's all, but the final answer is the same. Okay, so therefore this is the third and important axiom, which says that it's in fact a bimodule. Okay, good. So that proves this proposition. So this is a very important proposition in some sense. It says that if S and T had more structure, if M and N had more structure to begin with, they were S and T bimodules, then the resulting tensor product will also have more structure. Okay, now in particular, so let me just quickly mention some of the particular cases. If you only had one or the other, so there are many variations to this theme. So recall, so if suppose I am looking at M tensor N over R, so if M is an R module, right R module, this is a left R module, maybe only one of them has an additional structure. Now M can be an SR bimodule, and N could only be an R module. Okay. Now if that were the case, then the resulting object, the tensor product, in this case the tensor product becomes, well, there's only one structure that's left over, it's just an S module. Okay, because N didn't have any further additional structure, it was only a left R module. Okay. Of course, the best way to think about this is really in a unified fashion. So here's maybe a good explanation for why this happens. So think of it nevertheless as a bimodule. Okay, recall we have said this, if I have a left module R, I can think of it as a bimodule by just thinking of the right action by Z. So this is an SR module, that's an RZ module. Therefore, by what we have already said, the final answer, the tensor product, becomes an SZ module. Well, an SZ bimodule. Okay, but again, having a Z as one or the other component means, doesn't add anything extra to the structure. You already knew that your module, the underlying thing, was an abelian group, it was a Z module. That's the same Z module structure you are talking about. So the final answer is an SZ bimodule, but the Z doesn't add any additional information, so that's just the same as an S module. Okay, similarly, let's just look at the other variation. So if I had M tensor N and maybe M was a right R module, okay, it was a right R module, N was say some RT bimodule, then this means that the final end product M tensor N becomes only a right T module, if you wish. Okay, here when I say S module, I mean left S module. Okay, again, why is this the case? If M didn't have additional structure, I can always put a Z there. I can think of it as a ZR bimodule, and therefore the final end product becomes a ZT bimodule. Okay, so the final end product becomes a ZT bimodule, but the ZT bimodule is just the same as a right T module, because this Z here doesn't add any new information. We already knew this was, it's the same Z module structure. Okay, so these are all various ways of remembering this, and in particular this goes back to the original structure we had of tensor product. If m and n didn't have any further structure other than this was a right R module, this was a left R module, then I can just put z's on both sides. Think of this as a zr bimodule, that as an rz bimodule. So the end product is only a zz bimodule. Okay, and again the z puts no further structure here. It turns out just to be a z module. Okay, and that was the starting point really. Okay, so these are the, you know, this collection of facts about bimodules is very, very important, because usually it's not just the z module structure we are interested in. M and n will come with often with some additional structure. Okay, so we need to know how that is inherited by the tensor product.